We started this chapter by considering quantum mechanics in 3 dimensions. The first tool we used to solve problems, to solve the time-independent Schrödinger equation in 3 dimensions in particular, was separation of variables. We used separation of variables back in 1 dimension as well to separate the time evolution of an equation from the spatial evolution. That was how we got the time-independent Schrödinger equation from the time-dependent Schrödinger equation. In the case of 3-dimensional space, we also use separation of variables to separate the dimensions of space from each other. X from Y from Z, or in the case of spherical coordinates, which are most convenient for spherically symmetric potentials like we have for the case of the hydrogen atom, R from theta from phi. Another major difference between 3-dimensional space and 1-dimensional space is that in 3-dimensional space we have angular momentum. Angular momentum is not something that's going to fit into a single dimension, of course. So let's think about how angular momentum might behave in quantum mechanics. The approach we're going to take in this lecture uses operator algebra, the same sort of cleverness that we used back when we were talking about the quantum harmonic oscillator in 1 dimension with raising and lowering operators. We're going to take a very similar approach here. Back to basics though, first let's consider angular momentum. Angular momentum is what you have when you have an object and it's rotating about some axis. In classical physics, you're used to thinking about this as something like r times m times v, momentum and the radius, mvr. The best way of expressing this in classical physics is as L, which is a vector, is r vector cross with momentum vector, where r is the vector that goes from the axis to the object that's rotating, and p is the momentum, linear momentum, of the object that's rotating. We can make an analogous expression in quantum mechanics simply by replacing the arrows with hats. I know that's not terribly instructive, and we'll talk about that in more detail. But let's define a momentum operator, L hat, that's equal to r hat cross p hat, where p hat is a vector momentum operator and r hat is a vector position operator. Essentially, x hat, y hat, z hat as a vector crossed with px hat, py hat, pz hat, if I was writing things out in Cartesian coordinates. Now at this point I'm going to save myself a lot of writing and drop the hats. I'll try and make it clear as I write these things down what's an operator and what's not an operator, but for the most part in this lecture what I'm going to be working with are operators. This is an operator algebra lecture after all. So if you actually do the cross product between these x, y, and z operators, and these px, py, and pz operators, what you end up with is, well, you can do cross products, presumably. You end up with y hat pz, sorry, I was dropping the hats, wasn't I? Y pz minus z py, that's our x component. Z px minus x pz, that's our y component. And x py minus y px, that's our z component. Now these are all operators, and they're the same sort of thing that you're familiar with. Y, and I'll put the hat on in this case, is going to be y, the coordinate, multiplied by something. Whatever the operator is acting on, y hat acting on that is just going to be y, the coordinate, times whatever it's acting on, the function in this case. Likewise, for instance, py hat is minus I h bar partial derivative with respect to y of whatever the operator is acting on. So these are the usual operators. We're just combining them in a new way, in 3 dimensions. Now, as far as answering the question of how angular momentum behaves, one of the interesting questions is it quantized, for instance? How should we describe it? The approach that we're going to take here is motivated by, for instance, when we were talking about the position operator, we considered the eigenstates of the position operator. Those were the Dirac delta functions. Those were useful. If you consider eigenfunctions of the momentum operator in 1 dimension, you get plane wave states, states with definite momentum. And of course, if we're considering eigenstates of the Hamiltonian, those are the stationary states. Whatever the operator, if we consider the states, the eigenstates of that operator, we get states with a definite value of the observable associated with that operator. This is especially interesting to do in the case of angular momentum. So, I said this was an operator algebra question. How can we analyze the algebraic structure of the angular momentum operators? Well, I said angular momentum operators there, And there are going to be 3 of them. I'm going to break it down into Lx, Ly, and Lz in Cartesian coordinates because those are the coordinates that are most easy to work with. The way to think about these things in the operator algebra context is to think about commutators. And you'll see a very good example later on of why commutators are useful. But in this case, for instance, consider calculating the commutator of Lx and Ly. Now I know what the definitions of Lx and Ly are in terms of their Cartesian coordinates, so I can expand that out. Y pz minus z py, z px minus x pz. That's what I get for Lx, Ly. And from that, I'm going to subtract z px minus x pz and y pz minus z py. So this is Lx, Ly minus Ly, Lx, just by the definition of the commutator. If I expand out each of these terms, for instance, you'll get, if I expand the term from the product of these 2 terms in the expansion, I've got a y, I've got a z, I've got a pz, and I've got a px. All of these coordinates are in some sense different, except for pz and z. Back when we were talking about quantum mechanics in 3 dimensions, the very beginning of this chapter, we talked about the commutators of, for instance, pz and z being the same sort of commutator as you calculated in 1 dimension between, say, x and px. Y and pz, however, commute, as do y and px, z and py, etc. If the momentum and the position operators that you're considering are not the same coordinate, for instance, if I'm not talking about x and px, y and py, z and pz, the operators commute. So when I calculate the product here, y pz times z px, I have to keep the relative order of pz and z constant, but I can move the px and the y around wherever I want. What you end up getting for that, then, is something like this. I'll start at the left. This is going to be a kind of long and annoying expression. Apologies in advance. We're going to get a y, px, pz, z. So y, and I have to keep the pz and the z in order, and I'll put the px on the right, for instance. Actually, you know what? I'll save a simplification step here. I'm going to move the px to the left because I can do that. Px commutes with pz and z, and just write pz, z. And I'll put parentheses around them to signify that I have to keep them together in that order. The next term I get, multiplying across here, I have a y, I have a pz, I have an x, and I have a pz. So I have a pz and a pz, and pz of course commutes with itself. It doesn't even matter the order that I write pz and itself. So for this term, I'm going to get something like minus y, x, and I'll write pz, pz, just writing it down twice. If I keep expanding out these terms, minus z hat, minus z, z, py, 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 px. It's hard to read my notes here, since my handwriting on my notes is even messier than my handwriting on the screen. X, py, z, pz, in parentheses again, from the contribution of this term. Comes in with a plus sign because we have 2 minuses. The z and the x commute as needed, as does the py and the pz, but I have to keep the z and the pz in order, so I've got z, pz, x and py being pulled out front. That's for the top 2 terms here. For the bottom 2 terms, everything is going to have a relative minus sign. So I'm going to get a minus and y px, z pz, plus z, z, py, px, plus x, y, pz, pz, minus x, py, and then pz, z. So these are all my operators that I get as a result of expanding this out, provided I've copied everything down correctly from my notes. Now, if I've done things right here, you notice I have a z, z, py, px here, and a minus z, z, py, px here. So these 2 terms cancel out. I have a x, y, pz, pz here, and a y, x, pz, pz here. But x and y commute, so these 2 terms are actually the same as well, and they also cancel out. Another thing to notice here is here I have y px on the left. These 2 terms both have y px on the left. And on the right, I have things that don't commute, pzz and zpz. So this term here, I'll write it in black, I can combine these together. I'm going to have a y px, and then a pzz minus a zpz. And you know what that is. That's the commutator of pz and z, the operators. I can make the same sort of simplification over here. I have an xpy on the left, and I have a commutator of pz and z over here on the right, plus xpy z pz commutator, coming from these two terms. Now you know what the commutator of pz and z is. The commutator of z and pz is I h bar. This is the reason we like commutators. Commutator-like expressions often appear in expressions like this and allow us to simplify things, in this case just down to a constant. So this guy is going to be I h bar, and this, which is the same commutator only with the order reversed, is going to be minus I h bar. You can easily verify for yourself that swapping the order of the arguments in a commutator gives you minus the original commutator. So what I'm going to get now, at the end of all this, is y, where'd it go? I have a minus I h bar and I have an I h bar here, so I'm going to factor that out, and I'm going to have a y px and an x py, which should start looking familiar. Y px and x py appears in LZ. So this overall expression is just going to be I h bar LZ. So we started out calculating the commutator of Lx and Ly, and we got I h bar Lz. You can write down expressions for all of the commutators in this way. The commutator of Lx and Ly is I h bar Lz. The commutator of Ly and Lz is I h bar Lx. And the commutator of Lz and Lx is I h bar Ly. Likewise, if you swap the orders, you get minus signs. These are the commutators that are going to be useful to us in considering the algebra of angular momentum. If you feel the need to memorize formulas like this, note that the order these expressions always come in is always sort of cyclic, always sort of alphabetical. X to y to z and back to x. Here I have x, y, z. Here I have y, z, x. Here I have z, x, y. Always going around in this sort of clockwise order. You see a lot of sort of cyclic or anti-cyclic sort of permutation type arguments associated with commutators like this, and this is the first time that this sort of thing has shown up. So one thing you notice right away is that Lx, L, and Ly don't commute. We didn't get 0 for the right-hand side here. What that means is that if you want to determine simultaneously Lx and Ly, you have to consider the uncertainty relation between Lx and Ly. If I want to simultaneously determine Lx and Ly, the generalized uncertainty principle from the last chapter tells me that the product of the uncertainties in Lx and Ly is going to be given by the commutator of Lx and Ly. And if you go back to the previous page and figure out what that expression actually looks like, you get h bar squared over 4 times the expected value of Lz squared. So if I have some angular momentum in the z direction, I cannot simultaneously determine Lx and Ly. What that means is that if I'm considering angular momentum, I shouldn't be thinking about the angular momentum in the x direction or the angular momentum in the y direction. They're not very convenient observables to work with. What is actually a convenient observable to work with is L squared, which is defined to be the sum Lx squared plus Ly squared plus Lz squared. Essentially, the squared magnitude of the angular momentum, if you wanted to think about this in the classical context. This is sort of like saying r squared is the total length of a vector. So, the question then is, how does this L squared work? One thing you can do with this, L squared, since we're calculating commutators, is ask what's the commutator of L squared with, for example, Lz? Can I simultaneously determine one of my angular momentum direction coefficients with this total angular momentum squared sort of operator? What is this commutator equal to? Well, This L is going to be Lx squared plus Ly squared plus Lz squared, and we can separate out those commutators. Lx squared commutator with Lz plus commutator Ly squared commutator with Lz. And the third term is commutator of Lz squared with Lz. Now the commutator of Lz squared with Lz is just going to be 0. This term drops out. This is going to be Lz, Lz, Lz minus Lz, Lz, Lz. These two commutators we have to treat in a little more detail. So let's expand them out. This is going to be Lx, Lx, Lz minus Lz, Lx, Lx. And this is going to be Ly, Ly, Lz minus Lz, Ly, Ly. You can simplify this expression by adding and subtracting the sort of missing terms. If you think about this, here I have two x's on the end and Lz. What about Lz in the middle? So let's add and subtract Lz in the middle here. I'll write this as minus Lx, Lz, Lx plus Lx, Lz, Lx. So I haven't actually changed this expression any, I've just added and subtracted the same quantity. In the operator case, the addition and subtraction gets a little bit more difficult to understand, but this is essentially an identity. And I can do the same sort of thing here. I'll write minus Ly, Lz, Ly plus Ly, Lz, Ly. Now this we can actually work with. If you notice, here I have an Lx on the left, and then an Lx, Lz minus Lz, Lx. So if I was treating these two terms just by themselves, I could factor out an Lz on the left, and I would be left with a commutator of Lx and Lz. That would end up looking like this. So this is still an equality. Lx on the left, and then Lx commutator with Lz accounts for this term. This term is accounted for in much the same way, except I have to factor an Lx out to the right. So this is going to give me an Lx, Lz commutator with an Lx on the right. I can make the same sort of simplifications over here for exactly the same reasons, and I end up with pulling the Ly out to the left, Ly commutator with Lz, and pulling the Ly off to the right, Ly commutator with Lz, Ly on the right. So, still equal to my original expression. I haven't really made very much progress, but I know what the commutators of Lx and Lz are, or Ly and Lz. Those were the commutators I calculated on the last page. So this does actually simplify things out. The commutator of Lx and Lz is minus I h bar Ly. So this whole thing is going to be Lx. I'll stop writing it in square brackets because it's not a commutator anymore. Minus I h bar Ly. What I get for this commutator is the same. It's going to be minus I h bar Ly Lx plus, over here I've got Ly on the left, and these commutators are in alphabetical order, so I'm just getting positive I h bar plus I h bar Ly. Now, oops, I forgot where to go. I forgot my operator. The commutator of Ly and Lz is not just I h bar, it's I h bar Lx plus I h bar Lx Ly. Now, if you notice here, here I have an Lx followed by an Ly. I have to keep these in the right order because they don't commute, but I have a minus I h bar Lx Ly. I can bring the minus I h bar out front. Here, I have an I h bar Lx Ly. So, minus I h bar Lx Ly plus I h bar Lx Ly. These two terms cancel out. These two terms, here I have an Ly Lx, here I have an Ly Lx. Here I have a minus I h bar, here I have a plus I h bar. These two terms cancel out as well. So essentially what we're left with here, since everything is canceled, is 0, which means that L squared does commute with Lz. L squared commutator with Lz is equal to 0. This is the result that we'd hoped for. It means that we don't have a generalized uncertainty relation between Lz and L squared, which means I can simultaneously determine both L squared and Lz. That means I can hope to find eigenstates I can hope to find states that are both eigenstates of L squared and Lz. And that's really what we want. When we're done with this, we want something that's easy to work with, and eigenstates are especially easy to work with. So, we've worked out the general algebraic properties of angular momentum operators. And we've settled on working with this combination L squared and Lz. Those are operators that we can hope to work with. And what we're hoping to find are eigenstates, things that we can, most easily work with. So, how are we going to proceed? The way we're going to proceed is ladder operators. This is the same approach that we took back when we were doing the one-dimensional quantum harmonic oscillator. It was difficult to explain then, and it's difficult to explain now. Fundamentally, if we're working with L squared and Lz as our operators of interest, consider this just a definition. L plus or minus is equal to L sub x plus or minus I L sub y. These should look a little bit familiar, and we're in the end going to make the same sort of cleverness arguments that we made back when we were doing the quantum harmonic oscillator. But for now, let's just consider the properties of these L plus or minuses. We're doing algebra with operators, and we were calculating commutators. So let me ask you the question, what is Lz commutator with L plus or minus? Well, you can substitute in the definitions of Lz, L plus, and L minus. And since the commutator is linear, I can just split this up into two separate commutators. Lz commutator with Lx plus or minus I times Lz commutator with Ly. You know what both of these commutators are. We've already calculated them out. You get I h bar Ly plus or minus I times z and y here now are in the wrong order, so I'm actually going to get a minus I h bar Lx in this case. So this is our commutator, and if you simplify that down, you'll find that this is actually equal to plus or minus h bar L plus or minus. So calculating the commutator of Lz with L plus or minus gave me something relatively simple. It just gave me L plus or minus back. If I ask you the question, what is the commutator of L squared with L plus or minus? Again, you can expand out the definition of L plus or minus, L squared Lx plus or minus I times the commutator of L squared and Ly. But you know L squared commutes with Lx and L squared commutes with Ly. These are essentially the same as it commuted with Lz. So without even calculating anything here, we know the answer is 0. So this is the algebraic structure of these ladder operators. The key fact that I mentioned earlier is that what we're looking for are eigenstates of both of these operators simultaneously. Simultaneous eigenstates like that. Essentially, the question that we need to ask, then that we can use these ladder operators to answer, is if we have some state, and I'm just calling it f here, if L squared f is going to be given is an eigenvalue, if f is an eigenstate of L squared, it would have an eigenvalue lambda, for instance, and f is a simultaneous eigenstate of Lz, it would have an eigenvalue, for instance, mu. What about L plus or minus acting on f? Now the terminology here should be suggestive. I call these things ladder operators. Let's see what that actually gets us. First of all, consider L squared acting on this, L plus or minus f, acting on f. Well, you know that L plus or minus commutes with L squared, so I can write this as L plus or minus times L squared acting on f without changing anything. But L squared acting on f, I know what that is. It's just an eigenvalue multiplied by f. So this is L plus or minus times acting on lambda f. Lambda just being a constant can be pulled out front, so I've got lambda and then L plus or minus f. What this tells you is that L plus or minus f, if f is an eigenvalue, f is an eigenstate of L squared, L plus or minus f is also an eigenstate of L squared with the same eigenvalue. I can ask the same question of Lz what does Lz do to this mysterious quantity L plus or minus acting on F? This is a little bit more complicated, and I can simplify it by rewriting it slightly. Let's say this is Lz, L plus or minus. Now I'll write this as minus L plus or minus Lz plus L plus or minus Lz. I've just added and subtracted the quantity, and you can see what I'm trying to do now. I'm trying to arrange things such that I get commutators, as well as things that I know, because this is all acting on F, and I know what Lz does to F. It just gives me an eigenvalue. So this is now going to be the commutator of Lz and L plus or minus, acting on F, plus L plus or minus Lz acting on F. And I know what Lz does under these circumstances, since F is hypothetically an eigenstate of the Lz operator. It's just going to give me mu F back. This commutator, I also know how this behaves. This is Lz commutator with L plus or minus, which just gave me plus or minus h bar L plus or minus back. So overall, we're going to get plus or minus h bar L plus or minus acting on F plus mu L plus or minus acting on F. If I simplify that out, plus or minus h bar plus mu times L plus or minus acting on F. And again, what we got, L plus or minus, is still an if F is an eigenstate of Lz, L plus or minus F is also an eigenstate of Lz with a slightly different eigenvalue. L plus or minus acting on F was an eigenstate of L squared with the same eigenvalue, but for Z, L sub Z, we got a different eigenvalue. Notice specifically what this does. L plus or minus increases or decreases the eigenvalue of Lz. So if F is an eigenstate, L plus or minus acts to produce another eigenstate with a slightly increased or decreased eigenvalue in the case of Lz. And this increase goes with the plus, and the decrease goes with the minus. What this means is that we have a ladder of states. L squared, that's sort of like the total angular momentum. Lz, that's the z component. L plus or minus, then, changes Lz, essentially, but does not change L squared. Now, by saying something like changes Lz, what I really mean is that L plus or minus acting on an eigenstate of Lz gives you another eigenstate of Lz with a different eigenvalue. Likewise, if we have an eigenstate of L squared, L plus or minus gives you another eigenstate of L squared with the same eigenvalue. What this means is that if I apply L plus to an eigenstate of Lz, I'll get another eigenstate with an increased Lz. If I keep applying L plus over and over and over and over again, I'll keep increasing my Lz component. I can't possibly ever have an Lz component that's greater than the total angular momentum, though, which means we have to have a top. There must be a top. An uppermost state that I get by repeatedly applying L plus. In order for there to be a sort of termination to that sequence, there has to be a top state. And what I mean by that is that L plus, acting on this, and I'll call it Ft for F top, is equal to 0. This is the same as when we were working with the quantum harmonic oscillator and we applied the lowering operator, which gave us a state with lower and lower and lower and lower energy. As we keep applying it, if we're getting lower and lower and lower energy, there must be a bottom, there must be a lowest energy, there must be a lowest energy bound state in order to, enforce normalizability. So that lowest energy bound state had the same sort of expression. we applied an operator to it, in that case it was A minus, and we got 0. That was how we found our ground state. Here we're just working with the algebraic structure, and there are actually two ends in this case. We have a top, we also have to have a bottom. Since if I keep applying L minus over and over and over and over again, eventually I'll get a sufficiently large and negative angular momentum in the z direction that I'll start to exceed the total angular momentum, and that's going to be a problem as well. So there also must be some state that L minus acting on FB gives me 0. In order to get from FT to FB, I apply L minus. So I can lower my top state gradually, rung by rung by rung, getting all the way down to the bottom. So this is what I mean by there being some ladder of states. As far as working out what this ladder of states actually looks like and what the eigenvalues are, this is where we have to use an additional dosage of cleverness. We weren't done with cleverness when we were done with the one-dimensional quantum harmonic oscillator, unfortunately, and in this case, the approach is similar. What we're considering is the operators L squared and L sub z. When we were talking about the quantum harmonic oscillator, we were talking about the Hamiltonian operator, and we were able to express the Hamiltonian operator concisely in terms of the A plus and A minus, raising and lowering operators. In this case, we're able to express the total angular momentum squared operator concisely in terms of these L plus or minuses. So consider L plus or minus acting on L minus plus. What this is going to do should be reasonably clear if I lower and raise a state, or if I raise and lower a state first, depending on whether I'm going with the plus-minus combination or the minus-plus combination in the bottom. So let's consider what this looks like. L plus minus, L minus plus, as a combination of operators. I can express both of these in terms of Lx and Ly, Lx plus or minus I, Ly, and Lx minus or plus I, Ly. Simply, minus and plus, plus and minus. If I expand this out, I've got an Lx and an Lx, so I'm going to have an Lx squared. If I expand this term out, I've got a plus and a... Sorry, I neglected to swap my order there. A plus and a minus, an I and an I. So I've got one minus if I choose the top signs, and I've got an I squared if I choose the top signs. So that's going to mean I have a plus sign, plus Ly squared. Or alternatively, if I choose the bottom signs, I still have a minus and a plus. So I'm still going to get plus Ly squared, whether I choose the top signs or I choose the bottom signs. The remaining cross terms have Lx's and Ly's in them, and you can probably see maybe we're moving towards a commutator here. In fact, we are. What you get is minus or plus I times L... Where did my notation go? Lx, Ly minus Ly, Lx. And this commutator, you know what that is. That's I, H bar, Lz. So what we've got is this strange product of our raising and lowering operators gives us something that looks like a big chunk of L squared. So I'm actually going to rewrite this as L squared minus Lz squared. This is a positive step because Lz is something that I'm interested in. So I've got two things that I'm interested in now, L squared and Lz, instead of the things that I didn't actually care all that much about, Lx and Ly. So if I continue to simplify this, L squared minus Lz squared minus or plus, and now I've got an I and an I, so I'm going to have a minus 1 from that, so I'm going to change this minus or plus to a plus or minus, H bar Lz. Since what I'm actually interested in here isn't this strange combination, it's this L squared, I'm going to rearrange this and write L squared is equal to L plus or minus L minus plus Lz squared minus or plus H bar Lz. This is the expression that's going to come in handy for when we're considering the total angular momentum, for instance. When we're considering those top rung and bottom rung equations. So we know we have this ladder of states, and we know what the L plus and minus operators do to states that are on that ladder, either the top state or the bottom state, or some state somewhere in between, we now also have this expression for L squared, which is going to come in handy. So now, having derived this, let's go consider what our top rung actually looks like. The top rung, since what we're considering now are simultaneous eigenstates of both L squared and Lz, I have the following. I have Lz ft is equal to some eigenvalue, and I'm going to write this as h bar L times ft. You'll see why I'm using the L in a moment. Since this is a simultaneous eigenstate of Lz and L squared, I also have L squared ft is equal to, and I'll just leave this one as lambda ft. I also have my condition that I'm working with the top state here, which was L plus acting on ft is equal to 0. So now let's consider L squared ft in more detail. I have that expression that I derived for L squared on the last page. And there were actually two expressions there. I'm going to flip back for a moment. I have a choice here. I can choose the plus-minus combination or the minus-plus combination. And since in this case I know that I'm dealing with ft, I'm going to choose the combination where the plus acts first, because I know what L plus does to ft. So I'm going to write this L squared ft using the L minus, say minus, right, plus, characteristic of Brandt, L minus L plus combination plus Lz squared plus h bar Lz, all acting on ft. So I've just taken the bottom sign from the expression on the previous page for L squared. Now I know all of the terms here. If I expand this out, I have L minus L plus ft plus Lz squared ft plus h bar Lz ft. This guy, L plus ft, that's 0. So this term drops out. Lz acting on ft, I can write this as Lz, Lz, ft. Then I know what each of those Lz's does, just gives me an h bar L. So this is going to give me an h bar squared L squared ft. And this, well, this is just 1, so this is just going to give me an h bar squared L ft. So if I simplify this, what I get is h bar squared L plus 1 ft. This should start looking a little bit familiar, especially this L plus 1 combination. What this tells us essentially is that the eigenvalue lambda of L squared in this case is h bar squared L plus 1. So it's given us a relationship between L, the eigenvalue of the top, the eigenvalue of Lz for the top rung case, and the overall eigenvalue, the eigenvalue of the overall L squared, sort of the total angular momentum operator. So that's our top rung. Now let's consider the bottom rung. What does the bottom rung give us? Well, as before, we're working with simultaneous eigenstates of both Lz and L squared. So I have Lz f bottom is h bar, and I'll call this L bar in keeping with Griffith's notation for the eigenvalue of Lz. Likewise, L squared fb is equal to, and I'll leave it as lambda. Now keep in mind this is a different lambda than the one we had before, since we're dealing with a different state. And finally, L minus fb has to be equal to 0. That's what we mean by calling this the bottom rung. Lowering it gives you 0. You can't get any lower. So I can ask the same question that I asked in the case of the top rung. What is L squared acting on this bottom rung case? Since I know what the lowering operator does to the bottom rung case, I'm going to use my expression for L squared from a few slides ago that uses the lowering operator first. So L squared fb, substituting in my expression L plus L minus now, instead of L minus L plus like we used in the case of the top rung, plus Lz squared minus h bar Lz fb. So that's our expression. And once again, I know what each of these terms does. if I expand this out, L plus L minus FB plus LZ squared FB minus H bar LZ FB. Now L minus FB, as before, this is 0, so this term drops out. This term, LZ squared FB, I know what LZ FB does. It gives me this H bar L bar. So I'm going to have H bar squared and L bar squared FB from that term. And here again, minus H bar squared L bar FB. So when I simplify this down, I get a very similar looking expression. I get H bar squared times L bar plus 1, sorry, L bar minus 1 in this case, FB. This tells me that lambda, the eigenvalue in this case, is H bar squared L bar minus 1. So that's actually all we need. You know that since I have a different state, I might in principle have a different eigenvalue lambda here, but since we know that we're going to go from the bottom rung of our ladder to the top rung of our ladder and back by repeated applications of the L plus and L minus operators, which leave this eigenvalue unchanged, they don't affect the eigenvalue of L squared, what I'm going to get is the same eigenvalue. So this tells me that H bar squared L bar minus 1 has to be equal to H bar squared L plus 1. And that's actually the key, one of the key facts here. The structure of the eigenvalues we get here, as resulting from that, the L bar minus 1 equals L plus 1. The only way that this can be solved is if L bar is equal to minus L. If you substitute this into the original equation, you see it actually works. So if L bar is going to be minus L, that means we have the two ends of our ladder defined. Going from the bottom to the top. If I have LZ, the eigenvalue that I have for the bottom is going to be minus L H bar, and for the top is going to be L H bar. For the eigenvalue of L squared, then, what I'm going to get at the bottom is going to be H bar squared times, well, you know what's coming, L plus 1. And for the top, it's going to be the same, H bar squared L plus 1. And there are going to be some number of steps that I need to apply the L plus and L minus to go from either the top to the bottom or from the bottom to the top. So there are going to be, let's say, n steps. And this n, of course, has to be an integer. I can't apply an operator half of a time or 3/2 of a time. What that means is that L is going to be minus L plus n. The number of times I have to add H bar to minus L H bar to get L H bar. What that tells you is that L has to be that integer n divided by 2. So that's actually pretty much all you need to know. We have found our eigenvalues. L is going to be a half integer, so L is either going to be 0 or a half or 1 or 3/2, etc. And the eigenvalue for LZ is going to be something between minus L and L. If I write this as LZ acting on some state is M H bar times that state, M is going to be minus L up to L. Some number starting from minus L counting all the way up to L. This should look rather familiar. Back when we were talking about spherical harmonics, we ended up with a very similar structure for the allowed values of things which were incidentally called L and M. And it's not a coincidence. I didn't just choose the notation inconveniently. These are the same sort of numbers. But if you recall back to when we were talking about spherical harmonics, L had to be an integer. It was either 0 or 1 or 2 or 3. So in this case, we actually have these half-integer combinations, which are actually incredibly important for the concept of spin, which is going to end up being the next section. For now, to check your understanding, here are a couple of questions to consider to figure out whether or not you've really grokked the structure of these eigenvalues and what the ladder of states looks like. We started this chapter by considering quantum mechanics in 3 dimensions. The first tool we used to solve problems, to solve the time-independent Schrödinger equation in 3 dimensions in particular, was separation of variables. We used separation of variables back in 1 dimension as well to separate the time evolution of an equation from the spatial evolution. That was how we got the time-independent Schrödinger equation from the time-dependent Schrödinger equation. In the case of 3-dimensional space, we also use separation of variables to separate the dimensions of space from each other. X from Y from Z, or in the case of spherical coordinates, which are most convenient for spherically symmetric potentials like we have for the case of the hydrogen atom, R from theta from phi. Another major difference between 3-dimensional space and 1-dimensional space is that in 3-dimensional space we have angular momentum. Angular momentum is not something that's going to fit into a single dimension, of course. It's an operator algebra lecture after all. So if you actually do the cross product between these x, y, and z operators, and these px, py, and pz operators, what you end up with is, well, you can do cross product, presumably. You end up with y hat pz, sorry, I was dropping the hats, wasn't I? Y pz minus z py, that's our x component. Z px minus x pz, that's our y component. And x py minus y px, that's our z component. Now these are all operators, and they're the same sort of thing that you're familiar with. Y, and I'll put the hat on in this case, is going to be y, the coordinate multiplied by something. Whatever the operator is acting on, y hat acting on that is just going to be y, the coordinate times whatever it's acting on, the function in this case. Likewise, for instance, py hat is minus I h bar partial derivative with respect to y of whatever the operator is acting on. So these are the usual operators. We're just combining them in a new way, in 3 dimensions. Now, as far as answering the question of how angular momentum behaves, one of the interesting questions is it quantized, for instance? How should we describe it? The approach that we're going to take here is motivated by, for instance, when we were talking about the position operator, we considered the eigenstates of the position operator. Those were the Dirac delta functions. Those were useful. If you consider eigenfunctions of the momentum operator in 1 dimension, you get plane wave states, states with definite momentum. And of course, if we're considering eigenstates of the Hamiltonian, those are the states. So let's think about how angular momentum might behave in quantum mechanics. The approach we're going to take in this lecture uses operator algebra, the same sort of cleverness that we used back when we were talking about the quantum harmonic oscillator in 1 dimension with raising and lowering operators. We're going to take a very similar approach here. Back to basics though, first let's consider angular momentum. Angular momentum is what you have when you have an object and it's rotating about some axis. In classical physics, you're used to thinking about this as something like r times m times v, the momentum and the radius, mvr. The best way of expressing this in classical physics is as L, which is a vector, is r vector cross with momentum vector, where r is the vector that goes from the axis to the object that's rotating, and p is the momentum, linear momentum, of the object that's rotating. We can make an analogous expression in quantum mechanics simply by replacing the arrows with hats. I know that's not terribly instructive, and we'll talk about that in more detail. But let's define a momentum operator, L hat, that's equal to r hat cross p hat, where p hat is a vector momentum operator and r hat is a vector position operator. Essentially, x hat, y hat, z hat as a vector crossed with px hat, py hat, pz hat, if I was writing things out in Cartesian coordinates. Now at this point, I'm going to save myself a lot of writing and drop the hats. I'll try and make it clear as I write these things down what's an operator and what's not an operator, but for the most part in this lecture, what I'm going to be working with are operators. This is